So isomers, or there are three types: optical isomers, geometric isomers, and the conformational isomers. Optical isomers, there are again two types. One, they are enantiomers or diastereomers. Geometric isomers, cis-trans isomers. Conformational isomers, rotational isomers. They are called rotational. We call eclipsed configuration or staggered configuration. The chirality is a non-identical groups attached to the carbon atom. Carbon has four bonds. See, sp3 hybridized carbon is able to get connected to four groups. If all the four groups are different, and you can look at this picture, in the previous class itself, I have shown you some of the models, how this sp3 hybridized carbon is having the tetrahedral symmetry, and in the tetrahedral structure, all the corners are occupied by groups. And you can look at this particular diagram where this is the carbon, and these are all the four groups attached to the carbon. The bond angle between any two bonds in the carbon with sp3 hybridization is 109 degree 30 minutes. If all the four groups attached to this carbon are different, then this carbon is called chiral carbon or asymmetric carbon, and it has non-superimposable mirror images. And I have already shown you what is the actual meaning of non-superimposability. Superimpose means you are taking one more molecule like this and exactly keeping one over the other in such a way that the carbon and all other groups, they get matched and superimposed. If you get a chiral carbon and another molecule which is similar to the mirror image of this molecule, then the molecule and its mirror image cannot be superimposed. It is called a chirality. Non-superimposable mirror images. You can twist, you can rotate the molecule in any way. Only thing is you should not displace the bonds. You should not exchange the bonds. Without breaking the molecule, without exchanging the bonds, or without replacing the groups from one bond to the other bond, you should try to keep the molecule one over the other so that the groups will match. So such matching is not possible in the case of non-superimposable mirror images. So that is about the chirality. Chirality means it is asymmetry. So this carbon is called chiral, asymmetric carbon, and the molecule has chirality. Now, this is non-superimposable mirror image explained in a two-dimensional sheet. I'm taking a compound of type C, A, B, C, D. See, this A, B, C, D are the four different groups attached to the carbon. That is why I've tried to give four different colors for the groups attached to the carbon. Anyhow, the pink color is used for two groups where one group, the pink color is shaded, in another group, the pink color is given as a ring. And two more groups are green and red. Look at this first diagram. This is how a tetrahedron or a three-dimensional figure is explained, is drawn in a two-dimensional sheet. See the solid wedges, the horizontal solid wedges If the bond is drawn like this, that means that these two groups are projecting towards the viewer. If the bonds are drawn in dotted lines, this, this means that these two groups are away from the viewer. See, actually, these two bonds are not in the plane of your screen. Actually, it is projecting towards you. And also, these two groups are not in the plane of the screen. Actually, they are projecting away from the screen. So you are taking the mirror image. Normally in chemistry, the mirror is represented like this, one straight line with cross lines like this, slanting cross lines. This means a mirror. If a mirror is kept here, you will get the image of this compound like this. See, this pink color shaded comes over here because it's a mirror image. Whereas the pink color with a ring, it goes over there because it is a mirror image. Whereas the green inclined to your right in this compound is now inclining to your left. Similarly, here also the red group inclined to your right is now inclined to the left. So this is the mirror image of the compound of type CABCD. This is a chiral compound. Now these two compounds, suppose, let me say this is lactic acid. Lactic acid is the simplest optical isomer which can be studied easily. So this is lactic acid means, let me say this green is a COOH and this pink is OH and this pink ring is hydrogen and this red is methyl group. You can simply compare this structure which I have drawn at the bottom of the sheet and the top of the sheet. So look here. So these two are non-superimposable mirror images. They are chiral compounds. If you take this lactic acid and this lactic acid, what is the difference? Only difference is the OH and the H are interchanged. So no other difference. All other things are remaining the same. Here the OH is there. On this molecule, it is on the left hand side. The H is here. On the mirror image, it is on the right hand side. Nothing else is changed. Two groups are interchanged, and because of that interchanging, the two molecules are not superimposable. But if you study the physical and the chemical characteristics of these two compounds, I have already told you these two compounds have the same molecular formula. If you suppose if you want to write the molecular formula for this compound, what will be the molecular formula? It is C3O3 and then H6. So C3O3H6 for this and C3O3H6 for this also. So molecular formula is the same, and then its melting point is the same, its boiling point is the same, density is the same. If at all, if any refractive index is there, refractive index is also there. If you look into the chemical reactivity, suppose if you esterify, you can esterify this lactic acid with alcohol. So esterification, same, both the compounds will undergo esterification. If you do any decarboxylation, both the compounds will go decarboxylation. If you study any chemical reaction, they will be identical. If you study any physical properties, they will also be identical, but they are different. How they are different? They are different in their spatial positioning of the groups. So they are different only in spatial positioning of the group. And because of that, they actually do not show any fundamental physical difference or any chemical difference. So such compounds are called, they are isomers. They are optical isomers. But to be very specific, they are enantiomers. So the optical isomers which cannot be superimposed on each other and which have the mirror image relationship between them. They are called enantiomers. And the phenomena is called enantiomerism. So enantiomers. But if you take another compound, which is of the type CAABD, which means that two groups are the same. Look here, look at this picture. There is a pink ring and a pink shaded and two green. So these two groups are the same. Suppose I can replace this hydrogen with another OH. Then what will happen? This and this will be the same group. In such cases, the molecule becomes superimposable. If you take the mirror image, what will happen? See, this green is reflected over here and this green is reflected over there. Now what will happen? You can exactly keep this molecule over this so that all the four groups will get aligned. So this is a superimposable mirror image. So the molecules with a superimposable mirror image are called achiral. Achiral. Chiral means asymmetric carbon. Achiral means a symmetric carbon. And also, this asymmetric carbon is also called the stereogenic center. Stereogenic center. Or it is also called a stereogenic carbon. So, in order to explain the stereogenic center, the lactic acid molecule is drawn here. So a carbon is with the four bonds, where the four bonds are connected to four different groups, say COOH, OH, H, and CH3. So, but in order to mention that it is a stereogenic center, an asterisk mark is kept on the carbon. Now, this is what we have seen in the last class. I think you might have understood what I have told you. What is the proper axis of a symmetry? It is a rotational axis. Any molecule is containing an axis, and about that axis you can rotate the molecule. When you rotate for a certain degree, the groups will change their positions, and the resultant molecule, if it is identical with the original molecule taken, then the molecule is said to have proper axis of symmetry. In order to explain the concept of a proper axis of symmetry, the BCl3 molecule is taken. So in the last class, I explained this axis of symmetry with ammonia molecule, which is a pyramidal in shape. But BCl3 molecule is a planar in shape. The symmetry is a trigonal planar. So BCl3 molecule, it is exactly in your screen. B is at the center, one chlorine here, another chlorine here, another chlorine here. They are exactly separated by a distance of 120 degree because the boron undergoes sp2 hybridization. Sorry, it is sp3 hybridization, but one orbital is completely vacant. So there is no bond pair lone pair interaction. So the three hybridized orbitals, they get mutually extended in a spatial system. So they are getting arranged in a trigonal planar structure. Suppose if I assume an axis which is perpendicular to your screen and which passes through the boron, when you turn the molecule for an angle of 120 degree, see in this case, when you rotate the molecule, you should take care that you are not changing the direction of rotation in between. Suppose if you start rotating the molecule in the clockwise rotation, you continue in the clockwise for all rotations. Say one time clockwise and one time anti-clockwise, that will lead to confusion. So what will happen? So the BCl3 molecule, when it is rotated for an angle of 120 degree in the clockwise rotation, this chlorine, which is designated A, goes to the position of B, right? And the chlorine, which is B, goes to the chlorine C, and the chlorine C goes to the chlorine A. So that is simply the displacement. As a whole molecule, see, we are not breaking any bond, or we do not break this bond and keep over here. As a whole molecule, it is rotated. See, the very important condition in executing the symmetry operation is that you should not break any bond. You should not dismantle the molecule. As a whole molecule, you can rotate, you can reflect, you can invert, anything you can do, but you should not break and rejoin the bonds. So when you are rotating for an angle of 120 degree, the molecules are rotated and the new positions are occupied by the groups, and the resultant configuration is exactly identical with the original one. So as you have rotated 120 degree, where 120 degree is the minimum angle to be rotated to attain the first identical configuration. When you rotate for another 120 degree, what will happen? The chlorine, which is designated A, will come to the position of C. But when you rotate for another 120 degree, what you are getting is the same configuration. You should understand the difference between the same configuration and the identical configuration. Identical is not the same, but it is identical. It is looking alike. It is not the same. It is looking alike. So what will happen? As 120 is the minimum degree to be rotated to get the first identical configuration, the n, which is called the order of the proper axis of symmetry, is equal to 360 divided by theta, where theta is the minimum angle to be rotated to get the first identical configuration. So 360 degree divided by theta. So 360 divided by 120, you will be getting 3. So this axis is called C3 axis. So this is the proper axis of symmetry. Suppose if we take a water molecule is not a linear one. It is bent. Actually, the hybridization involved in oxygen in water molecule is also sp3. Ammonia, the hybridization involved in the nitrogen is also sp3. In methane, the hybridization involved in carbon is also sp3. But the difference is, in nitrogen, there is a lone pair. In oxygen, there are 2 lone pairs. In methane, there is no lone pair. All the 4 hybridized orbitals are ready for sharing their 1 electron with the other group. So because of the presence of the lone pair means a pair of electrons which are not involved in the bond formation. So in ammonia, it has 1 lone pair, and because of the presence of that 1 lone pair, the NH bonds are bent. That is why ammonia is assuming a pyramidal structure. Otherwise, it will be like boron trichloride, which is it is a planar triangular. Similarly, water molecule is bent shaped because of the 2 lone pairs. As it is bent shaped, you can assume an axis which is passing through the oxygen as it is drawn, and you can rotate the molecule in the clockwise direction. What will happen? The hydrogen B will go to the hydrogen A, and the hydrogen A will go to the position of hydrogen B. And what you are getting is an identical configuration. But when you rotate for the second time, 180 degree, what will happen? A will come back to its own position and B will come back to its own position. They are not identical, they are the same configuration. So this axis, the minimum angle to be rotated to get the first identical configuration is 180 degree. So the order of the axis n is equal to 360 divided by 180, which is equal to 2. So the order of the axis is 2. So already I have explained the plane of symmetry. What is a vertical plane? what is a horizontal plane, what is a dihedral plane, what is center of symmetry, and the improper axis of symmetry, you have to visualize a little more. Probably, if the college is reopened, I would like to teach all these symmetries with models so that you can very easily understand. Now you have to understand the difference between asymmetry and dissymmetry. This is a very important difference. Asymmetry means the molecule lacks all symmetry. It doesn't have any symmetry at all. That is called asymmetry, totally asymmetrical. Dissymmetry means it has proper axis of symmetry and it doesn't have improper axis of symmetry. First of all, you should understand the difference between the proper axis of symmetry and the improper axis of symmetry. In the proper axis of symmetry, when the molecule is rotated for an angle, you are getting an identical configuration. In the improper axis of symmetry, the molecule has to be rotated for a particular angle, and then the molecule has to be reflected about a plane which is perpendicular to the rotational axis. Both operations have to be performed to get the identical configuration. One rotation followed by a reflection. See, if improper axis of symmetry is not present and the molecule has a proper axis of symmetry, then that compound is called dissymmetrical. So because of the dissymmetry, the compound becomes optically active. And the asymmetric molecules are also optically active. But the symmetric molecules are optically inactive. So optical activity is observed in the asymmetrical molecules or dissymmetrical molecules, but it is not observed in the symmetric molecules. What is optical activity? So you should understand what is a light. Light is a wave sometimes, and it is a particle sometimes. This is what we study in quantum mechanics as the duality of light. Light has a dual character, double character. Sometimes it behaves as a wave, sometimes it behaves as a particle. Suppose if you take the concepts of diffraction, refraction, reflection, then the light behaves as a wave. But when you think of the photoelectric effect, which is the phenomenon in which the light of a suitable energy is falling on the polished metal surface, the electrons are ejected from the metal surface. This is something like knocking out of a coin in a carom board. So the light falls on the electron, which is assumed to be a particle in the metal surface. It is ejected out. This proves the this proves the particle nature of the light and the electron. Whereas if you think of wave nature, the diffraction, reflection, and other things are observed. It is a transverse wave. Transverse wave means the vibrations are perpendicular to the direction of a propagation of the wave. So if a straight line, you can assume a number of perpendiculars. So a light has its vibrations in infinite number of perpendicular axes to the direction of propagation. If the vibration is restricted to only one plane, then it is called a plane polarized light. So when this plane polarized light is passed through a solution containing an optically active substance, then the vibration plane will be shifted, will be turned either towards right or towards left. This is called optical activity. Suppose if you take two enantiomers, the enantiomers do not differ in physical characteristics or in chemical characteristics, but if you pass a plane polarized light towards through the enantiomers, one enantiomer will turn the plane of a plane polarized light towards right, and the other one will turn it towards left. That is the difference observed. How do these enantiomers differ? They differ in this particular property of turning the plane of a plane polarized light. If one enantiomer turns the plane of a plane polarized light towards left, the other enantiomer turns the plane of a plane polarized light towards right. That is the only difference. So, molecules having asymmetry and dissymmetry are optically active, but molecules having symmetry are optically inactive. In order to explain the asymmetry, two compounds are written here. One is called lactic acid, and the other one is called secondary butyl chloride. What is this secondary butyl chloride? See, one carbon is at the center, and one methyl group, and one ethyl group, and one hydrogen, and one chlorine are attached. Suppose if this molecule is written like this, C2H5 CHCl CH3 in one linear structure, you may not understand the existence of an asymmetric carbon in this compound. But when it is written like this, you are able to see that a carbon with asterisk mark is the asymmetric one, where four different groups are attached. Similarly, lactic acid, the four different groups attached to the carbon are OH, H, CH3, and COOH. Similarly, 2-methyl-1-butanol. This is another compound having asymmetry. So, one ethyl group, one methyl group, one CH2OH group, and one hydrogen. And for dissymmetry, you can take the following compounds as an example. See, this is called allene. Actually, this allene structure you can understand only with a model. Look here, in allene, this carbon is here. If this hydrogen and this chlorine are in the plane of the screen, then these two double bonds are perpendicular to that, and these two double bonds are in the plane of the screen, and these hydrogen and chlorine are perpendicular to the screen. It is something like a twisted model, perpendicular to the screen. Similarly, spiranes. These are spiranes. See the shaded, the darkly shaded portion are projecting towards the viewer, whereas the other portions are away. This is not a planar body. Similarly, biphenyls. They are called biphenyls. Two benzene rings attached by single bond, biphenyls. They can experience a free rotation, biphenyls. So these biphenyls, spiranes, and allenes, they are also optically active. But they are optically active because of dissymmetry. You can assume a dissymmetry in them, but they are not asymmetrical, they are dissymmetrical. So dissymmetrical substances are also optically active, but asymmetric substances are optically inactive. So these are the very important salient features to be discussed in this optical activity and the optical isomerism or enantiomerism. So what are enantiomers? They are compounds with the structures of mirror images, which cannot be superimposed on each other. If one enantiomer turns the plane of a plane polarized light towards right, the other one will turn towards left. That is the only difference we can observe about the enantiomers, but all other characteristics are found to be the same, the physical and the chemical characteristics. Their chemical reactions do not change, their physical properties do not change, except except this one particular characteristics. The turning of the plane of a plane polarized light. In all other properties, they are found to be identical. So they are called enantiomers. So